The largest steam locomotive ever built could burn through 10 tons of coal in a single hour. The strongest fireman alive could shovel roughly 1,200 pounds in that same time. It is not even close. Union Pacific's Big Boy was so enormous, so relentlessly hungry for fuel, that no human being could feed it fast enough to keep the boiler alive. So they built a machine to do the shoveling instead. That machine was not optional. Without it, the most powerful steam locomotive ever constructed could not turn a single wheel. And the reason it existed at all starts with a stretch of mountain railroad that pushed steel, steam, and human endurance to the breaking point. Union Pacific's Big Boy 4884 was not a one-off experiment or a publicity stunt. It was a fleet of giants, 25 in all, built for one of the most demanding jobs in North American railroading. Between 1941 and 1944, the American Locomotive Company, ALCO, out of Schenectady, New York, assembled these locomotives to meet a set of requirements that no existing engine could handle. The driving force behind the specification was Otto Jabelmann, Union Pacific's chief mechanical officer and a veteran of locomotive design. Jabelmann's team in the Department of Research and Mechanical Standards did not just want brute force. They needed a machine that could pull the heaviest wartime freight trains over the steepest grades and do it reliably, day after day. The Big Boy's wheel arrangement, 4884, was a direct response to the challenge. It had 4 pilot wheels up front to guide the engine into curves. It had 2 sets of 8 massive driving wheels to put every pound of power to the rails. It had 4 trailing wheels to support the enormous firebox. The articulated design allowed the locomotive to flex around mountain curves despite its size. At just over 132 feet long, including its tender, the Big Boy was the longest single-frame steam locomotive in the country. Production was split into 2 batches. The first 20 locomotives, numbered 4000 to 4019, rolled out in late 1941. A second order of 5, numbers 4020 to 4024, followed in 1944, after the War Production Board loosened restrictions on steel. Wartime shortages forced changes in materials. Medium carbon, quenched and tempered steel replaced some of the alloy parts, but the core design and performance targets never wavered. These machines were built as serious tools for a specific job, hauling heavy freight up and over the Wasatch Mountains. They were not museum pieces or engineering showpieces. From the start, the Big Boy was a production class, designed and delivered in numbers, each one expected to earn its keep on the rails. Today, 8 of the original 25 survive in museums, a testament to the scale and ambition of the project. But in the early 1940s, the Big Boy was simply the answer to a problem that no other locomotive could solve. The stretch of track that defined the Union Pacific's freight challenge ran from Ogden, Utah, up through the Wasatch Mountains toward the Wyoming border. This corridor, climbing over 2,500 feet in just 65 miles, was the operational bottleneck for the entire transcontinental route. The grades averaged 1.14%, with some sections reaching as much as 1.72%, enough to slow even the strongest locomotives of the day. Moving heavy wartime freight demanded more than just power. It required sustained, uninterrupted throughput. Union Pacific's goal was clear: run the longest, heaviest trains possible over the Wasatch without stopping to split them or add helper engines. Every time a train was broken into smaller sections or required double heading, it cost precious hours and tied up both crews and track space. Before the Big Boy, the standard approach involved using multiple locomotives, often pairing a 4.6/6.4 Challenger with another engine at the front or pushing from behind. This system worked, but it was inefficient. The process of coupling and uncoupling helpers, managing extra crews, and coordinating movements through mountain tunnels and sidings created a logistical headache. Wartime traffic only made the problem worse. Union Pacific's Department of Research and Mechanical Standards calculated that a single locomotive would need a starting tractive effort of at least 135,000 pounds of force to move a full-length, fully loaded freight train up the Wasatch grade without assistance. No existing locomotive could meet that requirement. The largest engines in service at the time, including the powerful Challengers, topped out well below the needed force. The Big Boy's design was engineered as a direct answer to this specific challenge. Its articulated frame, massive boiler, and expansive firebox were all sized to deliver the necessary horsepower and adhesion. This was not about breaking records for their own sake. It was about keeping trains moving, maximizing the line's capacity, and meeting the relentless demand for steel, coal, and wartime supplies headed west. The operational logic behind the Big Boy was rooted in efficiency. By eliminating the need for helpers, Union Pacific could reduce crew requirements, improve scheduling, and ensure that freight moved over the Wasatch with fewer delays. The stakes were measured in tons hauled, hours saved, and the ability to keep the nation's supply lines flowing at a critical moment in history. In this context, the Big Boy was not just a large locomotive. It was the railroad's solution to a mountain that refused to yield. Bulk was not a stylistic choice on the Big Boy. It was a necessity, written into every inch of steel. From the tip of its pilot to the end of its tender, the locomotive stretched 132 feet, 9¼ inches, a length that rivaled city buses parked end to end. This was not just the engine itself, but the full assembly including the tender, which alone carried the fuel and water needed to feed the monster's appetite. The sheer length was matched by raw mass. Depending on the subclass, a Big Boy weighed between 762,000 and 772,250 pounds. That is more than a fully loaded Boeing 747 on takeoff, all of it rolling on rails, designed in the late 19th century. Weight, in this case, was more than just a number. The locomotive's adhesive weight, over 540,000 pounds pressing down on its driving wheels, was the anchor that kept 135,375 pounds of tractive effort from simply spinning the wheels in place. On steep grades, adhesion is the difference between a train clawing its way uphill and wheels slipping uselessly on polished steel. The Big Boy's 12 driving axles distributed this force, allowing it to grip the rails with a tenacity that earlier engines could not match. This scale was not limited to the running gear. The firebox, the heart of any steam locomotive, dwarfed those found on conventional road engines. Where a standard 484 might have a grate area around 70 square feet, the Big Boy's firebox stretched to a confirmed 150 square feet, more than twice the size of many mainline locomotives. It was not just a matter of burning more coal. The vast firebox provided the heating surface needed to generate enough steam for the enormous cylinders, and its size dictated the entire rear half of the engine. 4 trailing wheels were needed just to support its weight. The firebox's width and length forced the boiler higher and the cab further back, reshaping the silhouette of the locomotive and demanding a tender that could keep up with its fuel and water consumption. Everything about the Big Boy's physical presence was dictated by the demands of its job. The long articulated frame, the massive boiler, the sprawling firebox, each was a structural response to the challenge of hauling thousands of tons over mountain grades. The result was a machine that looked outsized because it had to be, every dimension a direct answer to the problem of making enough steam, hour after hour, mile after mile. The firebox, in particular, would soon reveal the next limit: how to feed a furnace that no human could keep stoked by hand. At full output, the Big Boy's hunger for fuel became a force of nature in its own right. During heavy mountain service, the locomotive could devour between 10 and 12 tons of coal every hour, enough to fill a large dump truck. vanishing into the firebox in just 60 minutes. The water demand was even more staggering. On a hard run up the Wasatch, the boiler would consume about 20,000 gallons of water per hour. That's the equivalent of draining a backyard swimming pool every 3 minutes, all to keep the steam flowing at the pressure needed to move thousands of tons uphill. The numbers only grow more dramatic when broken down by distance. Under the stress of a full train and a steep grade, the big boy could burn through roughly 1,000 pounds of coal for every mile traveled. Each mile demanded a continuous, measured supply of fuel, not just a quick burst of shoveling. The firebox, with its 150 square feet of great area, acted as a giant furnace with a bottomless appetite. If the fire ever faltered, steam pressure would drop within minutes, threatening to stall the entire train halfway up the mountain. Power output on these runs reached an estimated 6,500 horsepower. That figure put the big boy in a class of its own among steam locomotives, delivering more than twice the horsepower of many mainline engines of the era. But that power came at a cost, a relentless need for energy, delivered in a steady, unbroken stream. The fireman's challenge was not to shovel faster in short bursts, but to maintain a constant, even fire that could keep the boiler at full pressure, mile after mile, hour after hour. The operational reality was simple and unforgiving. Steam could not be stored up for later. It had to be generated as fast as it was used. Every time the engineer opened the throttle, the demand for heat surged instantly. The firebox had to be fed continuously, or the pressure would collapse and the train would grind to a halt. There was no room for delay or uneven firing. The big boy's entire design depended on a continuous, industrial-scale flow of coal and water, an appetite so large that only a machine could hope to keep up. In this way, the big boy's daily operation was a race between fuel consumption and the limits of supply. The firebox could never be allowed to starve, not for a single mile, if the locomotive was to fulfill its role as the backbone of Union Pacific's mountain freight. This unending cycle of feeding and burning defined the big boy's working life and set the stage for the next challenge: the human cost of keeping such a fire alive. The fireman's job on a steam locomotive was always demanding, but the big boy turned it into a contest of endurance against physics. On most mainline engines, a skilled fireman could manage about 1,200 pounds of coal per hour over a long shift. That figure wasn't a matter of laziness or lack of grit. It was simply the upper limit of what a person could sustain hour after hour, shoveling from the tender into the firebox. Even the most robust fireman, working at peak effort, could only maintain higher rates for brief bursts, maybe a few minutes at a time. Tales of 10 tons in a shift sound impressive, but spread over 8 hours, the average still lands well below what the big boy demanded. The arithmetic was merciless. The firebox on the big boy stretched 150 square feet, wide enough that a man at one side could barely reach the far edge with a shovel. Keeping an even bed of coal across that expanse was a job that no single person could hope to handle, no matter how experienced. The locomotive's appetite for fuel wasn't just high, it was relentless. The fireman faced a moving target, with the engineer's throttle dictating sudden surges in steam demand. Every pound of coal had to be delivered on time and in the right place, or the fire would falter and the train would lose pressure. Adding a second fireman might seem like a solution, but the cab of a 4884 left little room for two men to work side by side in the heat and noise. The logistics of moving that much coal in that confined space made teamwork more hindrance than help. Even if two firemen could somehow coordinate their efforts, their combined output still fell short of the firebox's hunger. The gap between human ability and machine need was simply too wide to bridge by muscle alone. This wasn't a failure of the men who worked the rails. It was a matter of scale. The big boy's design pushed past the point where human labor could keep up, not because the crews lacked skill or willpower, but because the numbers no longer added up. The job had outgrown the worker. Only a machine, relentless and tireless, could shovel fast enough to keep the fire alive. Union Pacific specified the standard type MB mechanical stoker as standard equipment on every big boy locomotive from the very first unit. This was not an aftermarket upgrade or a luxury for convenience. It was a fundamental part of the design, as essential as the boiler or the wheels. The reason was simple arithmetic. The firebox's 150 square feet of grate demanded a steady, industrial-scale supply of coal, far beyond what any fireman, or even a team of firemen, could shovel by hand. At full power, the big boy's appetite climbed to 10 or 12 tons of coal per hour. The only way to keep that fire alive was to mechanize the entire process. The standard MB stoker transformed coal handling from a test of human endurance into a powered, continuous operation. Coal, drawn from the tender, was moved by machinery directly into the firebox, eliminating the need for a fireman to hurl shovelfuls across a space nearly 8 feet wide and over 19 feet long. This mechanical solution was not a nod to comfort or a way to make the job easier. It was an operational necessity. Without it, the big boy could not have delivered the uninterrupted power required for mountain freight service. By integrating the stoker into the core of its design, Union Pacific acknowledged the fundamental limit of human labor in the age of supersized steam. The big boy stoker was not just a tool for efficiency, it was the only way the locomotive could fulfill its intended role. The result was a machine that, for all its power, depended on another machine just to keep its own fire burning. In that dependence lay the real measure of how far steam technology had pushed the boundaries of what was possible, and how close it had come to the edge. Coal entered the big boy's firebox not by shovel, but by a machine designed to match the scale of the locomotive itself. The process began in the tender, where tons of coal rested in a steel bunker. At the bottom of this bunker, a large screw-shaped auger powered by the locomotive's air compressor turned steadily. As it rotated, the auger drew coal forward, moving it from the tender toward the firebox, with a force and consistency that no human crew could hope to match. Once the coal reached the front of the tender, it dropped into a feed chute leading into the stoker's delivery system. Here, the coal met a set of steam jet spreaders, nozzles that blasted jets of steam at carefully controlled pressure. These jets did more than just push the coal forward. They broke up clumps, atomized the fuel, and hurled it in a wide arc across the enormous firebox. Instead of landing in a single heap, the coal fanned out, reaching all corners of the 150 square foot grate. Feed chutes and pipes guided the coal steam mixture through the final stretch. Some chutes directed fuel to the front of the firebox, others to the sides or rear. This arrangement allowed the firemen to ensure that every part of the grate received fresh coal, preventing hot spots or dead zones that could lead to uneven burning or wasted fuel. The goal was always the same: a deep, even bed of glowing coal burning steadily from edge to edge. Control rested with the fireman, but the job had changed. Instead of shoveling, he now stood at a dedicated stoker lever in the cab. By adjusting this control, he could speed up or slow down the auger, increase or decrease the force of the steam jets, and fine-tune the rate at which coal entered the firebox. When the engineer called for more power, the fireman responded by opening the stoker, feeding more coal into the flames. If the train coasted or the throttle eased, he dialed the feedback, maintaining just enough fire to keep steam pressure steady. The system's true advantage lay in its ability to keep the fire uniform. On a locomotive as large as the big boy, A patchy or thin fire could bring steam pressure down in minutes, stalling the entire train on a grade. The mechanical stoker made it possible to maintain a thick, even firebed mile after mile, regardless of how much coal was needed. It was a machine built to serve another machine, a powered, tireless arm feeding fuel to a rolling furnace that never rested as long as the train was in motion. The big boy's appetite for coal and water was matched only by the scale of its rolling supply base, the tender. Unlike the small tenders trailing earlier steam engines, the big boy's tender was a behemoth in its own right. It carried 28 tons of semi-bituminous coal, enough to fill a small rail car, and 25,000 gallons of water, more than a typical backyard swimming pool holds by a factor of 30. Without these vast reserves, the locomotive's massive firebox and boiler would have run dry long before reaching the summit of the Wasatch. Supporting such weight required a special solution. The tender rolled on a 14-wheel centipede design, with 4 leading wheels and 10 trailing wheels spread across multiple trucks. This arrangement distributed the immense load evenly, preventing the rails from buckling under the combined force of coal, water, and steel. Fully loaded, the tender itself weighed over 164,000 pounds, as much as a modern diesel locomotive. Its length, nearly 40 feet from end to end, made it a fixture as substantial as the engine it supplied. The tender was far more than a passive trailer. It functioned as an integrated supply base engineered specifically to keep the big boy running at full power for hours at a time. The coal bunker was positioned to feed the mechanical stoker directly, minimizing the distance fuel had to travel before reaching the firebox. Water tanks were baffled and reinforced, allowing the locomotive to draw thousands of gallons per hour without sloshing or sudden surges that could destabilize the train. Every detail, from the placement of the fill hatches to the arrangement of the discharge pipes, was designed for speed and efficiency during refueling stops. Engine and tender worked as a single operating system. Without the tender's capacity, the big boy would have been forced to halt for coal and water every few miles, negating the very purpose of its design. Together, they formed a self-contained unit, one that could cross mountain ranges without assistance, carrying its own reserves for the long haul. This unity of engine and tender was essential to the big boy's role as the backbone of Union Pacific's busiest freight corridor. The arrival of the mechanical stoker did not mean the fireman's work vanished. It changed the nature of the job. Instead of swinging a shovel, the fireman now stood at the controls, hands on a set of levers and valves that governed the stoker's every move. His responsibility became one of constant adjustment and attention. The feed rate of coal had to match the engineer's throttle and the locomotive's demand for steam, which could change in seconds as the train climbed a grade or coasted downhill. Too much coal, and the firebox would choke and waste fuel. Too little, and steam pressure would drop, threatening the train's progress. The fireman watched the firebed through small openings, always looking for signs of uneven burning or clinkers, hard lumps of fused ash that could smother the fire. If a jam developed in the auger, it was his job to catch it early, using a combination of sound, vibration, and experience to sense when the steady flow of coal was interrupted. Clearing a blockage or adjusting the steam jets that spread coal across the grate required quick thinking and a steady hand. The stoker's machinery, while powerful, could not compensate for neglect or inattention. Airflow was another critical variable. The firemen managed the fire door openings and the dampers that controlled how much air entered the firebox. Too much draft could cool the fire and waste heat. Too little would stifle combustion and produce smoke instead of power. Each adjustment, whether to the coal feed, the air supply, or the firing pattern, had to be coordinated with the train's speed, the grade of the track, and the engineer's demands. On the big boy, automation meant oversight, not relief from skill. The fireman became a systems operator, responsible for the health of a living machine that could only run at its best when every part was in balance. The job demanded vigilance, judgment, and a deep understanding of how fire, air, steel, and steam worked together at a scale few people ever experienced. In the heat and noise of the cab, the fireman's role was transformed, but never diminished by the machine that now shoveled coal in his place. Scaling steam power to the size of the big boy was an engineering triumph, but not a miracle of efficiency. The locomotive's thermal performance, measured in how much energy it could extract from every ton of coal, did not outpace smaller engines of its era. In fact, the big boy's overall efficiency rarely exceeded that of Union Pacific's 484s, or Challengers. What set it apart was not how little fuel it used, but how much work it could do. Moving thousands of tons up a mountain, hour after hour. That power came with a price. Every new system added to the locomotive, every extra set of wheels, the massive boiler, the intricate stoker, meant more moving parts, more wear, and more opportunities for breakdown. Maintenance logs from the 1950s show that stoker-related repairs alone accounted for about 5% of all service hours on the class. Auger jams, steam jet erosion, and the constant need to clean and adjust the coal delivery system kept shop crews busy. The mechanical stoker, essential as it was, introduced its own set of problems that demanded regular attention. The big boy's true achievement lay in its ability to deliver raw pulling power on a scale no other steam locomotive could match. But this was not a path toward ever greater efficiency. Each increase in size brought diminishing returns. The locomotive could do extraordinary work, but only with heavy upkeep and a constant supply of fuel and water. The more steam was scaled, the more apparent the penalties became, in the form of complexity, maintenance, and the hard limits of what could be sustained on the rails. The big boy stands as the ultimate expression of steam technology pushed to its outer boundary. Its need for a mechanical stoker wasn't just a clever solution. It was the unmistakable sign that the age of steam had reached its practical ceiling. Here was a locomotive so powerful, so demanding, that it required another machine simply to keep its own fire alive. The stoker became the emblem of this threshold, a device that transformed the fireman's job from raw physical labor to the careful management of a mechanized system, all to satisfy an appetite for fuel that no person could sustain. Every aspect of the big boy's design, its massive firebox, its towering boiler, its endless hunger for coal and water, spoke to the limits of what steam could achieve when scaled to the extreme. The paradox at the heart of the big boy dissolves into a broader truth, that there is a point where engineering ambition meets the hard boundary of human and mechanical possibility. The big boy was beautiful, formidable, and in the end, a machine built at the very edge of what steam could ever be asked to do. Diesel locomotives arrived on the Union Pacific with a promise that steam giants could not match: lower cost, simpler upkeep, and a streamlined crew. Where the big boy demanded a fireman to manage the stoker and a constant cycle of coal and water. A diesel engine ran with only an engineer, sometimes a single helper for long runs. There was no firebox to clean, no boiler to maintain, no tender to refill every 100 miles. Fueling a diesel meant topping off a tank, a process that took minutes instead of hours. Internal studies from the 1950s laid out the numbers in black and white. On a per-ton-mile basis, steam cost Union Pacific about 12 cents, while diesel cut that figure to just under 5 cents. Maintenance hours per 1,000 miles dropped by more than half. The diesel fleet could stay on the rails longer, with fewer breakdowns and less time in the shop. For every big boy that needed a team to keep it running, a string of diesels could do the same work with fewer hands and less fuss. Admiration for the big boy's power never faded, but the logic of the railroad business was unyielding. Between 1959 and 1962, Union Pacific retired the entire class from revenue service. The decision was not about sentiment or spectacle. It was about the hard math of cost, reliability, and the changing shape of American railroading. Today, preserved big boys stand silent. They are monuments to a moment when human ambition outpaced human strength. As automation defines more of our world, the line between what we dream and what our bodies can deliver grows wider. The big boy's mechanical stoker is not just a relic. It is a reminder that every leap in power demands a new kind of partnership. Some challenges are too big for muscle alone. Thanks for joining me on this journey.